Hello and welcome to another episode of Maths in an Empty Classroom with me, Mr. Southern. This is slightly different to usual. I'm less front-facing on this one, but in this video we are going to be looking at modelling with logarithms, and the example that I'm going to be going through with you today is taken from the edXL Pearson Year 1 textbook. So here we are then. First example, we have the table below gives the rank by size and population of the UK's largest cities and districts. London is ranked number 1 but has been excluded as an outlier because of the size of the population being so much greater. So there the table shows you those 5 cities: Birmingham, Leeds, Glasgow, Sheffield and Bradford, with their ranks from 2 to 6 and then their population, each of which has been rounded to 2 significant figures. The suggestion is that the relationship between the rank and population can be modelled by the formula P equals AR to the power of n, where A and n are constants. So this is the type of relationship that's suggested between the rank R and the population P. And the first thing we're being asked to do is to draw a table giving values of log R and log P to 2 decimal places. So all that's required for that is to log each value in the table, base 10, and to draw up a separate table with those values. So I've just cut the one from the book, and you can see it there. So here are your log R values going across here. And here are your log P values. And what we're going to do is we're going to investigate the relationship between these 2 sets of values to try to give us an indication of what the relationship is between P and R. So now the textbook is asking you to plot a graph of R against log R against log P, and draw a line of best fit. We are going to do that, but we're going to be a little bit we're going to do a little bit better than that. So what I've done is in Desmos, I have drawn a graph of the original data. So on the x-axis here, we have the values 2, 3, 4, 5, 6 for the ranks of the cities, and on the y-axis we have the population. So starting with 1 million, going down to 480,000. And as you can see here, we've got what would appear to be quite a nice, smooth, curved relationship going on here. What then happens when you use the log values from your table is if we put log of R on the x-axis and log of P on the y-axis, then we get this rather lovely, what looks like a very, very linear relationship here. And what the textbook is asking is you to draw a line of best fit and use that to find the values of A and N. I'm going to do it like I am going to do that, but I'm going to do it instead using the class whiz. So what I'm going to do is come back into here. And on the class whiz, what I'm going to do is I'm going to go menu 6, y equals a plus bx, which is the regression equation of a regression line. And I'm going to enter the log R data in for x and the log P data in for y, and then ask it to do the regression calculations for me. So I do that by pressing Option and then number 4 for regression calculations. And what that tells me is that A equals 6.1919, B equals negative 0.667, and R equals negative 0.9976. So let's just talk about this value for a moment, this value of R. That is pretty spectacular. To have a value of negative 0.99, that indicates that it is almost perfect negative correlation. And if I just take you back to the graph, you can see how that's going to be pretty much a straight line. And what that value of R indicates is that when we get that line drawn on, those points are going to line up onto that line pretty much perfectly. So because we're using y equals a plus bx, what we can do is we can now write that y equals 6.19 minus 0.67 x. And what I've done with both of those, the a value and the b value, is I've rounded them to 2 decimal places because the original data that we're using has been rounded. So that should be the equation of the regression line, which is the relationship between the log r and log p. So if I go back into Desmos, what I'm just going to do on this one here is I'm going to type in that information. So I'm going to type in y equals 6.19 minus 0.67 x, and as you can see, I've got a linear graph here, pretty much perfectly going through all those points. So the relationship between log p and log r I found to be a linear relationship, which is great. So just coming back into here then, what I need to realize is that although I've used y and x for my axis in Desmos, what this is actually relating to is y axis represents log p, and the x-axis is represented by log r. And what I need to do is I need to, from this equation here, get it into this form, p equals a r to the power of n, because if I know the value of a and the value of n, I'll be able to find the equation of the original curve on the previous Desmos version. Now, it is possible to manipulate this equation to get it into this form here, but what is far, far better to do, in my opinion, is to start with this equation here, p equals a r to the power of n, and rearrange it so that it looks like this. Now, how I'm going to do that is I'm going to take logs of both sides. Now, the fact that I'm not writing any base implies that it's base 10. And then I'm going to separate out the right-hand side using my rules of logarithms. So the first one I'm going to use is the addition rule of logarithms to write it as log a plus log r to the power of n. And then I'm going to use the powers rule of logarithms to write it as log a plus n log r. And what I'm now going to do is write that equation underneath this one over here. So log p is equal to log a plus n log r. And what that allows me to do is to compare what I've got in the equation that I found for the regression line with the general form in logarithms of this equation, p equals a r to the power of n. So what I can see is I've got log p for both. I've then got 6.19 and log a. So what I can conclude from that is that log a is equal to 6.19. And then the other thing I've got here is I've got log r in both cases, but here where I've got n, I've now got negative 0.67. So from this, I can conclude that n is equal to negative 0.67. Now, just looking at this one here, I've got log of a is 6.19. I want a value for a. Now, I know that this is base 10, because when you just write log, that's what that means. So a is going to be 10 to the power of 6.19, which is 1548816.619. Now, I am not going to use that whole value here because the original data was rounded to 2 significant figures. I'm going to round my value of a to 2 significant figures. So I'm going to say that that rounds to 1,500,000. So 1.5 million, 1,500,000, and that's to 2 significant figures, matching the accuracy in my original data. So what that allows me to do then, if I come back to this equation, p equals a r to the power of n, I can now write that p is equal to a, which I now know to be 1.5 million, r to the power of n, so r to the power of n, which I've calculated to be negative 0.67. So what I've now done is I've found the value of a and I've found the value of n. So I'm suggesting that the non-linear relationship between r and p will fit this formula here. P equals 1,500,000 r to the power of negative 0.67. So what I'm just going to come and do now is go back to the original Desmos graph that I drew with the original data. And we suggested that there was this non-linear, pretty nice relationship going on here. So what I'm just going to do is enter in the equation to test this out. So I'm going to use y is 1.5 million x to the power of negative 0.67. And as you can see, that curve is pretty close to those points there. It's not on it as close as the linear graph that we've got on our other Desmos tab. The reason for that is we've rounded this value of A fairly significantly, but we needed to do that to fit in with our original data. So what we would be able to do now is if we were given the value of R, the rank for another city, we would be able to substitute that in for X in this equation to find an estimate for the population. So there we go. We were given some information about the rank and the population. We logged both sets of data and used our regression function to find a linear relationship, which was this equation here. And we then used logarithms to get our non-linear relationship into an equivalent form and compared to find the values we needed to get our non-linear equation. There we go, job done.